ID the Future, a podcast about evolution and intelligent design.
Welcome to ID the Future. I'm Andrew McDermott. Today, host Eric Anderson concludes a two-part conversation with Dr. Bijan Nemati about the search for habitable planets. Whether you believe there's intelligent life elsewhere in the universe or not, Dr. Nemati says we can all be excited about the quest to answer this age-old question. In this second half of the conversation, Nemati continues to discuss his work on the Roman Space Telescope, set to launch within the next 2 years. He also shares some intriguing details about another future probe currently in the works called the Habitable Worlds Observatory, including how these state-of-the-art probes will work together to identify and learn more about exoplanets in space that have the potential to harbor life. Dr. Nemati is an astrophysicist working at NASA's Jet Propulsion Laboratory. As such, his discussion will get quite technical at times. But hang in there and enjoy the complexity. This is an update about an exciting area of space exploration that you don't want to miss. Here's Eric Anderson once again to continue the conversation.
Okay, so Roman's going up sometime. We're not announcing anything today, but in a couple of years, 2026, 27, sometime in there, we'll get Roman launched.
Yeah, and so here's the way to think about it in terms of numbers. In terms of what a fancy term in this field called contrast, and contrast is the ratio of the peak of the planet signal to the star signal, and peak to peak, it's those numbers like a billion that we talked about. Roman is supposed to be able to get its requirement was only it needs to be able to see a planet with a contrast of 10 million.
Okay,
10 million times dimmer. So when we've met that requirement, we know that we have that. But now, if it does better, it has the capability to do better. And if all goes well on orbit, when we do test it out in a couple of years, it's conceivable it could go down almost in the few times 10 to the minus 9. In other words, in the billion class.
Okay.
And then HWO needs to be in the 10 billion class, 1 in 10 billion. And so if all goes well, we are only a factor of 10 or so, maybe, a little more than a factor of 10, but that level away from what we need to be for Earth detection.
Okay, yeah. In terms of size and position, you mean? Again, we're not
now,
talking about other factors. Yeah.
Yeah, you mentioned position. I have to say, though, with a caveat, that at the wavelengths we are operating, we can't get too close to the star. So we would not, even if we went down to 10 billion, we couldn't see an Earth.
Okay.
Because the Earth is too close to the star, and that does require an HWO for sure.
Sure. Okay. So talk to us about, we're using this term HWO. So Habitable Worlds Observatory is what we're talking. That's the current name. Who knows if the name will be changed in the next few years, but
I'm sure it will.
That's okay. That's the current name we're going with, HWO. So tell us now what it's going to do to increase the sensitivity, increase our capability. And then also, I think there was a discussion about specifically searching for signs of life on some selected number of exoplanets that have been designated.
Yeah, Habitable Worlds needs to be big, but it already, its precursors were a couple of concept studies, actually 3 concept studies, in which the bigger one was 15 meters in diameter. And frankly, that was just that's not realistic. I mean, that is my guess is that would have been, hundreds of billions of dollars. It's just the decadal committee said, yeah, that's nice, but it's not going to happen in this century. So let's not worry about that. But then they said, let's do something more modest, like a 6-meter telescope. With that, you can still probably see, like we said before, about a couple of dozen, if you look at 100 stars, that are just very crudely in the class of Earth-sized planets. But then to do that, what does this telescope have to do? Well, first of all, you have to decide, because you're trying to manipulate the electric field of the light on the focal plane. To do that, you have to start with something pretty near perfect. And when you have a telescope like the Webb, let's just pretend, what if the Webb with a coronagraph bolted onto it? Can't we just do that? And we've done that kind of thing before. The Mars rovers built on a successful design, and they just changed the instrumentation, and they did like 2 or 3 missions. But here it requires a significant, as great as the Webb is as a telescope, and they did beautifully, it is an infrared telescope. And in fact, kind of goes into the, deeper infrared where the wavelengths are large, and at the larger wavelengths,
a lot more forgiving.
Yeah, more forgiving, because relative to it's like how good you have to make the telescope mirrors is always like compared to the wavelength of the light they're using. And if you have to be 100th of a wavelength or 10th of a wavelength, well, a tenth of, a big number is a bigger number than a tenth of a small number. And so in the visible, you have to just do a lot better. But that's not really the big problem. The big problem that HWO, or Habitable Worlds, needs to solve is how do you keep this telescope stable long enough? Because what really happens with these coronagraphs is that when you've done all you can and you have arrived at your best solution for the deformable mirror, and you get your dark zone is really dark and you're now looking for a planet, you'll see, let's say there is a planet. Let's say you see the planet light in your images. But you know what else you'll see is these speckles, these blobs of leftover light that you did not succeed in fully taking out. The average level is, let's say, a factor of 10 billion less than the star. You did, on average, do okay. But it's still kind of this at the 1 in 10 billion level, there's just faint little speckle in the background. Now, if that speckle is stable, then you say, I've been seeing these speckles the whole time. I know what they look like. I'm just going to subtract it from the image, and I'm going to look for a planet. But what if those speckles are not stable? They move around. And now, is this a planet? Is it a speckle? And that is a very big technical problem. And in all the sort of like the internal meetings, it's all the most intense discussions and arguments and all that are held over what constitutes a design of a telescope that would be the Habitable Worlds design that would most promote stable speckles. And also, what technologies could we invoke that the instability that there is there we could somehow measure? And I can go into some of that detail, but I'll stop here and let you kind of drive it, because I can go down that rabbit hole deep.
Yeah. We'll be here all day, right? Talking about speckles.
Yeah.
No, that's fantastic. So, but in any event, just at a little higher level. So remind me how big Roman is?
Roman is 2.36 meters.
Okay, so 2.36, and we're going up to 6 meters.
Yeah.
Like James Webb, except we're now moving into the visible spectrum instead of infrared. So we've got to have much better mirrors.
Yeah. More forgiving. You don't need to cool it the way James Webb does, but now unforgiving, because now you have to keep it super stable.
Fair enough. So you've got trade-offs, right? Mm-hmm. And Habitable Worlds is going to be located where? Lagrange 2?
Yeah, just like the Webb.
Okay, explain that to people who may not know.
Yeah, there is a stable position called the second Lagrange point, where a satellite or telescope, for telescopes it's great, where you can have a stable orbit, but also an orbit that's so far away from the Earth that the Earth itself doesn't produce a lot of heat load on the telescope. So all this stuff about speckle instability, well, if you're going in front of or behind the Earth as you're orbiting the Earth, if as a satellite or a telescope, well, every time you do that, you just get a snap or a shock of heat, heat and cold, and you would never have the kind of stability you need. So you have to be where, the Earth shine, as it were, and Earth eclipsing is just like not a factor.
Right. Okay. So it's pretty far out. I mean, we're talking vastly farther out than the low Earth orbit type of instruments. And it also helps a little bit, doesn't it, Bijan, with stability, and that you can kind of park it out there. You don't have to use a lot of fuel to keep it in the right place, or am I misunderstanding that once you're there?
Yeah, once you're there, I think that it's not extraordinarily difficult to be stably in orbit, and so that should not be a particular problem.
Yeah.
But I think the thermal stability, that aspect of its stability, is particularly valuable.
Right. Okay, great. All right. So Habitable Worlds will be out at Lagrange 2. It's going to have this large 6-meter mirror that we can get into the optical range. We don't have to worry about some of the effects of the Earth being close by. And they're looking specifically, at least at this early stage. Again, the mission's got years before it rolls out and launches. But at the early stage, the idea is we're going to select a couple dozen planets, I think 25, they said, focus in on those and really look at them carefully and see if we can find signs of life on these 25 exoplanets.
That's right.
And have these been identified, or, I mean, there's still years to go, so maybe some would be bumped up in priority, or how's that?
I think some of that will probably happen. I think, we know what sun-like stars there are in the sense that we know the spectral type of the stars nearby. But if transits or other techniques give us hints that some stars are better candidates than others, we'll look there. One of the things that actually I'm going to bring up now for the first time is there is another complication, but not a complication, a noise source that's very important, and that is dust. Planetary systems have dust. The Earth itself has dust in the region amongst the planets. So this forms something that's called zodiacal light. And there's this glow that you have at a faint level, very faint. But when we're talking about these kinds of effects and these very, very faint signals, for detecting let's call it an exo-Earth around an exo-sun, in other words, an Earth-like planet around a sun-like star, if it were there, the glow from the dust, the ZODI as they call it, is actually the largest source of photon noise, or basically random noise that there's going to be.
Interesting.
And the reason that's important is that the Earth may be, though we don't know for sure, special in yet another way, is that the amount of dust we have in our solar system may be on the very low side compared to typical planetary systems. Okay. And if that's the case, what if the typical planetary system has 10 times our level of ZODI, or zodiacal dust? Now, suddenly we have a sort of a major amount of random noise source. Now, random noise, there's one thing good about random noise, which is that if you just wait there and take more and more images for longer and longer period of time, then average them, the noise will go down because the ups and downs of the noisy things will actually average out to a smooth number. Mm-hmm. But that does mean you have to take a long time to take an image. And then it's very funny how a 5-year mission, suddenly you find like, I don't even have time for 25 planets. Right. It's like, so that's a very important question. And whereas Roman, previously I said, was a technology demonstrator, I think one of the very huge important things that Roman will do for HWO is that the Roman coronagraph is capable of shedding a lot of light into which targets, which stellar, observational targets might have, really, really bad zodiacal dust.
Okay.
And which ones may not. And so in the target selection, there are things we don't know that Roman will help us find out.
Okay, very interesting. So you're talking about zodiacal dust in the target. Does the dust here locally impact things?
Yeah, the dust here is an issue, but it's not as big an issue as the dust on the far side, particularly for, looking for Earths. Because if you think about it, if there's a source of light, the star, shining light on something, the farther away that something is, it's like 1 over the radius squared. It's less of the starlight falls on it. So these dust particles, as you approach the star, the dust particles that are near the star, which would be like where an Earth would be, are much, much brighter than the dust particles that are far from the star. So, for example, the Earth is 5 times closer to our sun than Jupiter is. So this means that if I was looking at an exo-Earth compared to an exo-Jupiter, I'm looking at 25 times more this background fuzzy, glow that I need to overcome. And when I'm looking for an Earth compared to when I'm looking for a Jupiter. So looking for an Earth is tough in this way.
Interesting. Okay, Bijan, so we've been talking about this technology primarily as it relates to what you've been working on with the coronagraph, but there was also some discussion of a different technology for habitable worlds potentially, right?
That's right. A coronagraph technically does all the magic that it does internal to its machinery, internal to its optics. It blanks out a star, so that's called an occulter. The occulter means makes it dark, makes it black. And so that's called an internal occulter. You can have an external occulter. An external occulter goes by the name of star shade. And the star shade technology is a whole different approach to this. You now think about something that looks like a circle in the sky. It's like a umbrella that you open up in space. And the umbrella has a diameter of the size of a baseball field. It's like 35 meters or something like that. And this thing you fly at about 50,000 kilometers away from you. And then you fly in formation. You want to look at star X, you essentially command the umbrella, the star shade, to go out and put itself between you and that star. And then there's a lot of detailed adjustment alignment.
Oh, imagine.
And then finally, when the detail is done, suddenly that star is gone, and it's gone very decisively, and you can see planets around it. The beauty of the star shade is that its demand on the telescope is minimal. The telescope now can be what we would call affectionately a light bucket. All it does is collects light. It doesn't have to be fancy. The optics don't have to be that great. The sensor has to be good, but no active optics the way we talk about coronagraphs. Where do you pay for all that advantage? You pay for it by the fact that when you want to go to see a star over the other direction on the sky, that occulter has to make a very long journey in space. It has to fly. And you'll run out of propellant. So then you have to figure out, how am I going to get more propellant to this thing to take it from one place to another? So typical mission scenarios with star shades maybe can budget, I don't know, something like a few dozen stars, or maybe 10, not more than 10 dozen before it would run out of gas, as it were. But it's a very, I'd say the jury's out on whether that's the best approach or a chronograph's the best approach.
And requires some incredibly precise formation flying between the two of them, it would seem.
That's right. And that will need to be shown.
Now, has Starshade been used before? Or is this...
No. That has never been done in space as far as I know.
I hadn't heard of it either.
And I'm pretty sure it hasn't. Yeah, but what I do know, and I have pretty close friendship with some of the inventors of this, and this has been very successfully demonstrated in the lab. And in the lab, it's kind of interesting. How do you demonstrate something like this? Well, your baseball field size, and now it's about the size of the palm of your hand, and it's in a tube that's an extremely long tube, and you mimic that on a very, very small scale. Then there's also experiments that have been done in, like, can you unfurl a very thin sheet with metal superstructure from something compact out to something very big? That has been done successfully.
Sure, yeah.
So that's kind of where things are with that.
Very interesting. Okay, one last technical question. You can keep this one short, and then I wanted to ask you just one sort of more high-level question to wrap up. But my technical question is, what about micrometeorites and damage to the mirror? And
yes, yeah. Early in James Webb's life, it got a hit from micrometeorites. And from the design meetings that I'm attending, we are pretty much already kind of realizing, whereas for James Webb, that worked out, it's going to do okay. We can't afford to do this with the HWO. The next telescope will have a tube again. And that will dramatically reduce the likelihood of those incidents.
Okay.
So, yeah.
Good. All right. So, well, this has been absolutely fascinating. I've been like a kid in a candy store today. I really appreciate having an opportunity to kind of pick your brain as someone who's been working on this for a decade and still working on Roman and HWO coming up. This is super exciting. So really, really appreciate it. I do want to ask you just sort of one question related to ID. I mean, how in your mind, as an ID proponent and somebody who's working on this, how does all this relate to intelligent design, and what can we expect, and what are you excited about?
Yeah, I think that with regard to design, there's sort of two sides to it. There's a kind of the rareness of the Earth question. And like you yourself actually nicely pointed out earlier in our conversation, that from a design perspective, the Earth could be rare or common. We're not really tied to either conclusion. A designer could design many times. But if I'm positing no design, then I really need to, as the design filter tries, first basically says, is it chance? Is it law? Mm-hmm. And the counterpoint to that is that, well, if it isn't design, there better be a decent amount of chance, and there should be, if there is not a law. And none of us would say that there are laws in the universe, because, nobody thinks that the laws in the universe are driving, Earths to occur every single time, because we see that's not happening.
Yeah.
But probabilistically, people go there. And so just gaining statistics on planetary characteristics and other planets is just very valuable in this debate. Secondly, the day may come where an HWO telescope is up there and it sees a signal. And it sees a signal which is from a planet. The planet is orbiting a sun-like star. And let's say it's an Earth-class planet. And in fact, they get a spectrum from the star. Now, the ultimate desire is to kind of invoke something like what's called the Lovelock test or Lovelock idea. Lovelock, I forgot his first name right now, but I think it's James, maybe? Yeah. He basically posited that if you find in such a test, when you're looking at the atmosphere of another planet, a couple of kinds of elements or a couple of chemicals, I should say, that would normally not be in equilibrium, that they would eat each other up, but they seem to be both there in abundance, then they are probably being constantly produced so that they can stay in that disequilibrium state. And for example, if you have ozone and methane, well, that might be from life, And so the day will come that we will be asking these kinds of questions, may come where we would be asking these questions. And I think some of the good work that we could all be doing, whichever side of this we are, is putting the Lovelock idea to the test. What are the geological processes that could account for some of these things? And do we really have anything that really could be a smoking gun? And if it is, what kind of certainty does that give us? That would be an interesting area of study.
Absolutely. Well, thank you so much, Bijan. This has been absolutely fascinating. Really enjoyed spending time with you today, and so excited about the work that you're doing. And again, congratulations on shipping out today. And we'll be looking for, we'll be looking for a launch announcement here in a couple of years.
Yeah, we're all excited. Thank you so much, Eric.
You bet. Appreciate having you. Thank you for listening to this episode of ID the Future. To find out more about our place in the universe, please visit us again at idthefuture.com or check out our sister YouTube channel, Discovery Science. For ID the Future, I'm Eric Anderson. Thanks for listening.
That was Eric Anderson speaking with Dr. Bijan Nemati about the search for habitable planets. Don't miss part 1 of this conversation, where Dr. Nemati provides an overview of exoplanet discoveries of the last 25 years, including how the technology for finding exoplanets has advanced. If you enjoy the content you hear on ID the Future, take a minute to leave a positive rating and review on Apple Podcasts. Just search Intelligent Design the Future in the Apple Podcasts app and leave us a review. Your efforts are going to help us reach new listeners with the powerful arguments for intelligent design. For now, and for ID the Future, I'm Andrew McDermott. Thanks for tuning in.
Visit us at idthefuture.com and intelligentdesign.org. This program is copyright Discovery Institute and recorded by its Center for Science and Culture.